Hello, today we are introducing Arenes. So I'm going to talk you through some key ideas and then leave you to have a look at the PowerPoints, fill in your need to know sheet and have a look about naming some of these structures. So arenes are going to be the group of molecules that are going to contain a benzene ring that we've often seen drawn out like that. So what we need to look at first is how we basically came to a structure that looks like that. So it's a little bit different to what we might expect. So the formula of benzene is C6H6. So let me zoom you in a bit closer there. There we go, C6H6. So we have 6 carbons joined in a ring. The fact that we've got a low carbon to hydrogen ratio suggests you're going to have a ring here. 6 hydrogens. So we need to bond each of those on like that. And then that means that each carbon has only formed 3 bonds. So in order for each of them to form 4 bonds, we might put in a series of double bonds like that. So if you then go through and count what we've got there, each carbon has 4 bonds. This is what we call the Kekule structure. Okay, so this was the initial structure that was proposed for benzene. However, researchers found that many of the things that you might predict should happen from a structure like this didn't actually happen with benzene. One example, if we've got carbon-carbon double bonds, we expect to have an addition reaction with bromine water, and you would decolorize your bromine water. However, it was found that this doesn't happen with benzene. So these carbon-carbon double bonds aren't behaving in the conventional sense. It was also found by using X-ray diffraction that all of the carbon-carbon bond lengths in benzene are the same. Now, what we would expect from this structure is that we'd have alternating long bonds for our single bonds and short bonds for our double bonds, where because we've got twice as many shared electrons, we've got a greater attraction between the positive nuclei and the bonding electrons, pulling those atoms in closer together. But the reality shows that all of these carbon-carbon bond lengths are equivalent. So what we need to have a think about is how that comes about. So if we consider to start with an alkene, so we'll consider ethene. So we have carbon with 2 hydrogens attached to it like that. And then sigma bonded to another carbon and it's 2 hydrogens. So our 4 outer shell electrons, 3 of them are now occupied in bonding. And our 4th electron is in a pz orbital perpendicular to the plane of the other molecules there. And we have learnt before that we have the overlap, the sideways overlap of these, which can then allow us to have our pi bond. So basically that is denoting our pi bond. And we often draw this out more correctly to show the final structure as having the kind of sausage shapes above and below. So these make up the pi bond here. So the 3 sigma bonds for each carbon, and then we've got the pi bond above and below. Now, if we take that idea and put it onto benzene, you end up with a bit of a chaotic diagram, which will be drawn much more clearly on the PowerPoint. Don't worry about having to draw my hopeless one out here. But if we take our hexagon, and I'm going to try and draw it with wedges and dashes here so that you can imagine this kind of in the plane of the page, hopefully. So let me just put our carbons on there to keep those in. Now, each of those carbons, in the same way as like we were looking at with the ethene there, is going to have a hydrogen bonded on like this. So we've got sigma bonds keeping the ring together and bonding the hydrogens. Now, each of those carbons has that 4th electron in the pz orbital. So I'm now going to draw those on like this. And just like the ethene, these can overlap. But which are going to overlap? So we could say that these 2 pz orbitals overlap, then these 2, and these 2 which might give us what we're drawing out here. But there's nothing to say that that is the way it has to happen, because this one could overlap with this one instead, then these two, and then these two. And so what happens in reality is that you get a pi cloud of electron density, whereas all of these are merging, forming your pi cloud of electron density that's then above and below the plane of the molecule. So we could sort of, like we did the squiggles up here, we could join all the top lobes together like that. And I have some different colours out here. Let me use a different colour. And then we could have the bottom lobes. Oh, try one actually works. The bottom lobes joined together there. So hopefully you can see we've got a top ring and we've got a bottom ring there. And that is the pi cloud of electron density. Now, because these are all now delocalized, we can say that the pi cloud over here is localized because it just sits between those two carbons. But here the pi cloud is spread across all the carbons here. So this is a delocalized pi cloud of electron density. And that leads to our increased stability. Now, the key bits of evidence about the stability came from comparison of the hydrogenation enthalpies. So if we were to have cyclohexene like this, and we were to react that with hydrogen, we would produce cyclohexane like that. So on account of that, it wouldn't be unreasonable to expect that if we take the KKLA structure of benzene like that and react it with 3 moles of hydrogen, we would also get cyclohexane like that. And it would lead on from that if we said that the enthalpy change for that top reaction was equal to minus 120 kilojoules per mole, as we've got this structure here, 3 times the number of carbon-carbon double bonds, it would lead on that we might expect to get 3 times the energy released on reaction. Now, when this is actually carried out, what is found is that when we take benzene, so I'm now going to put it with its standard symbol there with the circle in between. That's denoting the delocalized pi cloud of electrons. And we react it with the 3 lots of hydrogen that are still needed to produce our cyclohexane like that. That in reality, we get minus 208 kilojoules per mole of energy released. Now, we've talked about previously how we can use energy level diagrams to indicate the different stabilities of things. So we can then have a think about this in terms of an energy level diagram. So if I draw my axes out there and actually move them so you can see them. Where's the bottom? There we go. Okay, so if we've got energy on our y-axis, and we often just put progress of reaction on our x-axis down there, then the product in every case here is the same. So we have got cyclohexane as our product. And we can then use our energies to work out where our various benzene structures should be in the first place. So the reality, the actual benzene, releases minus 208 kilojoules when it's hydrogenated. So it must, we'll just put that one there. So we'll call that minus 208. And we'll say that this is real benzene plus 3H2. If we then add on our KKLA structure, that released minus 360 kilojoules per mole. So that was our theoretical value there, assuming the KKLA structure and the 3 times the energy release compared with cyclohexene. So again, 3H2, so same product, and that one was minus 360. And again, we've talked before about the fact that if something is of lower energy, it is of greater stability. So our actual structure of benzene has a greater stability than the theoretical KKLA structure here. and that is indicated by the fact that we get less energy out in our reaction overall. And then we can think of that in terms as well of if we were thinking of breaking all the bonds in order to be able to rearrange everything and make our products, we could kind of think about how much energy it takes to get up to producing atoms at the top. And that links in with the activation energy idea as well. So if we were trying to get to our atoms, we'd have to put in that amount of energy before coming back down the other side for our actual benzene. But with our, yes, that's for our actual benzene. But for our Kekulé structure, we could put in a lesser amount of energy before coming down here. So if we have to put in less energy to break something up, then again, it suggests it's less stable in the first place. So the fact that actual benzene, the one with the ring, is of lower energy, suggests it's got a greater stability, and then that can be linked with the fact that you've got to put more energy in to break it, and then we get the same amount of energy back out when our new product bonds form. So it kind of links in with your bond energy ideas from earlier in the course. So we have our structure there. We could also think about the overall shape of benzene. So I'm just going to go back up to the top here. So you should remember from your alkene work that the alkenes are a planar, a flat structure, and here we would have our 120-degree bond angles. And we're going to have the same over here. So this is going to be a flat planar structure. So we have a flat molecule, and then you have your pi cloud of electron density above, and then your pi cloud, the other kind of part of your pi cloud underneath there. Okay, so true ways of denoting this, and you'll see mixtures. So if we are going to draw out the displayed formula, then you ought to put in all your carbons. So draw everything in like that. Draw in your hydrogens. And watch me draw some hydrogens here. There we go. So that would be our displayed formula. If we want to have the skeletal formula, then hexagon with a circle in the middle. So this is denoting that pi cloud of electron density. And you just have to remember each of those carbons is bonded to one hydrogen. And although this structure here would suggest the Kekulé structure, you do see it written down quite a lot. It will feature on exam papers. They do seem to use both, but what they mean is the delocalized pi cloud of electron density rather than the localized version that this would imply. One more thing just before we disappear from this one is that actually this structure here can be used along with the arrow pushing, so our curly arrows, to actually kind of see how we get the delocalized version. If we were to draw some curly arrows on here, so say we want our carbon-carbon double bonds to move. If we move our pair of electrons here from the pi clouds and put them here, that would then mean we've got too many electrons around this carbon. So it means that this bond has to break and the electrons have to go over there. Too many electrons around here, so this bond's going to have to break and they're going to have to go around there. Unfortunately, these shifted in the first place to kick all that whole thing off. So we could then draw this structure out and then shift the double bonds all round one. So can we see how from there I've got to here? And then once we're here, of course we could do the same and we could shift all these along. And that would simply take us back to where we were in the first place. And although you don't need to know this explicitly, for the exams, it kind of helps back up this idea of the stability. We call these resonant structures. And the greater number of resonant structures you have, and that basically means the greater number of ways you can arrange your electrons to have the same general structure, and the greater the stability something has. So because these electrons are free to move around, we have the two resonant structures, and that is what allows us to have this pi cloud of electron density, because the orbitals are sufficiently positioned that we can have free movement of the electrons all the way around. Okay, so you now need to carry on with the PowerPoint. So there's a little bit, there's lots of bits to fill in that will go over the key theory we've been talking about here. And then you need to have a look at naming and have a bit of a practice of naming. And then we'll come back later with another video that will tell you about the reactions.